Hey guys, here are the notes for section 7.4, day 1. 7.4 is all about working with trigonometric identities. We did this before previously when we were working with the trig functions. Just remember, an identity is literally a statement of equality. All right, it's saying that this is equal to that. So that if you have to, you can interchange one trig function in an equation for another trig function that is something of equality. Okay, so an identity. Two functions f and g are identically equal if f of x equals g of x for every value of x for which both functions are defined, right? F of x and g of x have to be equal to one another for every single value you could possibly plug into these functions that are in both domains, right? That's an identity, as long as the left side is equal to the right side all the time. All right, such an equation is called an identity. An equation that is not an identity is called a conditional equation. All right, so for example, if you have 2 times the quantity x plus 5 equals 2x plus 10. Well, if I was to distribute my 2, I would literally get 2x plus 10. So that's an identity because the left side will always equal the right side no matter who you plug in for x. If I plug in x is 5 here and x is 5 there, the left side will always equal the right side. That's an identity, right? Here, cosine squared theta plus sine squared theta, it always equals 1. It doesn't matter what you plug in for theta, whatever angle you plug in, the cosine of angle theta squared plus the sine of angle theta squared, it's always going to equal 1, no matter who theta is. All right, that's an identity. However, if you look at this equation, 3x plus 1 equals 10. The left side will only equal the right side if x is 3. So that's what a conditional equation looks like. The left and the right side are only equal to each other under a certain condition. The condition here being that x has to be 3. The left side will not equal the right side for every single value of x you plug in. Okay, same thing here. The sine of angle x equals 1. That's a conditional equation because it'll only be true when x is pi over 2, because that's the angle who has a sine of 1, or if you are an angle that lands in the same spot as pi over 2, you will make the equation true. But the left side of this equation will not equal the right side for any value of x that you plug in. Okay, so we're going to be working with identities. Equations where the left side will always equal the right side no matter what you plug in for x, okay? So let me go over some of your identities, some of your statements of equality, all right? Trigonometric identities are statements of equalities that are going to allow us to rewrite one trig function in terms of another trig function. All right, we have our quotient identities. Remember, the tangent function is defined by the sine divided by the cosine. So if you have the tangent function in a problem, you could take that out and put in sine theta divided by cosine theta because they are equal for any value of any angle you plug in for theta. All right? Same thing, if you have this in an equation, you could take that out and put tangent theta in its place. They are interchangeable because they are an identity. All right, you have another quotient, the cotangent of angle theta is equal to, well, cotangent is the reciprocal of tangent. So if this is your tangent ratio, well, then your cotangent ratio is the reciprocal, so it is cosine over sine. All right, you have your reciprocal identities. The cosecant is the reciprocal of sine, so it's 1 over sine theta. The secant is the reciprocal of cosine, so it's 1 over cosine theta. The cotangent is the reciprocal of tangent, so it's 1 over tangent theta. All of these are statements of equality. I could take this out of the equation and put this in its place, or I could take this out of the equation and put that in its place. These are interchangeable statements of equality. All right, then we have all of our Pythagorean identities, and they all start with the mom and dad, right? The cosine squared theta plus sine squared theta equals 1. And then if you manipulate him, you get all the rest of your Pythagorean identities. So all of these are statements of equality. So these are things that you could take out and put other things in inside of an equation, okay? All right, you have your sine, your even and odd identities. If you remember, the sine and the tangent were odd functions. So if you take the sine of the opposite of theta, well, then the opposite ratio comes out. If you plug the opposite of your input in, then the opposite of the original output comes out. That's odd function behavior, right? If x went in and y came out, well, then you plug the opposite of x in, the opposite of y comes out. That's odd function behavior. So if you ever have this written in a problem, you could take it out and put this in its place. All right, the cosecant of the opposite of theta is equal to the opposite of the cosecant of theta. All right, cosine was even. So when x goes in and y comes out, when the opposite of x goes in, the same y still comes out. That's even function behavior. So the cosine of the opposite of theta equals cosine theta. It equals the same ratio as just cosine theta. All right, the secant, his reciprocal, is also an even function. So the secant of the opposite of theta is equal to the secant of just theta. All right, and then like I said, the tangent is an odd function. So the tangent of the opposite of theta equals the opposite of tangent theta. The cotangent of the opposite of theta is equal to the opposite of cotangent theta. So these are all identities that you might find yourself looking back and saying, all right, who can I take out and what can I put in its place? So keep this handy because it'll help you a lot. All right, here we go. In this section, the goal in this section is to establish new identities, new statements of equality by algebraically manipulating trig expressions. Some techniques to do this will be demonstrated in the following examples, okay? Here are 4 basic algebraic techniques that we use to simplify trigonometric expressions, okay? Number 1, I'll never forget my pre-calc teacher telling me this, is a lot of times you're just trying to rewrite everything you can in terms of sines and cosines. All right, so get your tangents out, put sines and cosines in and whatnot. All right, so one technique you're gonna use is rewriting a trig expression in terms of sine and cosine only. All right. Another technique you might be asked to use to simplify these trigonometric expressions or to prove an identity is to multiply the numerator and denominator of a ratio, of a fraction, by a well-chosen value of 1. Well, what does that mean, right? Think conjugates. Guys, think about this expression right here. If I asked you guys to rationalize 3 over 5 plus radical 7, right, there's nothing to do. You can't really divide that, but we don't leave irrational numbers in our denominator. We don't leave the root 7. So to get rid of it, you would times the bottom and top by the conjugate 5 minus root 7. Well, guys, guess what? 5 minus root 7 over 5 minus root 7, that's 1. That's a well-chosen value of 1. When you choose to multiply this by his conjugate, you are picking a well-chosen value of 1 to multiply the top and bottom of this fraction by. All right, so think conjugates when you want to be told to do that. All right, number 3. Another technique you might use is writing the sums of trig ratios as a single ratio. So basically, if you're adding, subtracting fractions, if they're asking you to add and subtract fractions, which is a ratio, then add them together. Get a common denominator, add them together, and make one fraction. All right. And then another technique you might use is factoring. A lot of difference of 2 squares. Remember, a squared minus b squared always factors to a plus b and a minus b. And then a lot of GCFs. What do these terms have in common? All right, is another technique you might use. And I added another one. Our book doesn't really stress this technique, but the old pre-calc book did. And I feel like it allows you to do some problems a lot easier. So just remember, when you have a proportion, right? 1 fraction equals 1 fraction, cross multiplying is a great approach because a lot of times it'll help you to avoid making a complex fraction. It'll help you avoid having fractions within fractions. Again, our book doesn't always show this way, but it's still a great way to know because he comes in handy. All right, so today all I'm going to do is run through 4 examples with you, and then the day 2 notes will go over the rest of the examples. And then guys, we're done. This is it. This is the last section. All right, here we go. So it says in this example, simplify cotangent theta divided by cosecant theta. We want to simplify this expression by rewriting each trig function in terms of sines and cosine functions. So we want to try and get this to be an easier function to work with. So we're going to simplify it by rewriting everything in terms of sines and cosines, right? So cotangent theta can be rewritten as cosine theta divided by sine theta, because right, that's the definition of the cotangent function. He is the cosine divided by the sine. All right, and then I'm going to divide it by the cosecant of angle theta can be rewritten as 1 over sine theta. So I've taken the original expression and I've rewritten it entirely in terms of equivalent statements, and those statements are made up entirely of sines and cosines. So now all you have to do is simplify this complex fraction. So I'm going to multiply by the bottom reciprocal, and then I have to multiply the top by that same as well, right? So what happens down here? Cancels, cancels. Up here, cancel, cancel. You're left with cosine theta over 1, which at the end of the day is just cosine theta. So you have turned this trigonometric expression into a simplified version. You have reduced it to just the cosine of angle theta. So basically, the cotangent of theta divided by the cosecant of theta will equal the cosine of that angle of that theta for any theta you plug in within their domains. So you have turned this expression into an equivalent, simpler version. So this is your answer. Okay, so a lot of times I feel like when in doubt, try and get as many sines and cosines as you can in, and then stuff like this starts to happen. Magic starts happening, and you can cancel stuff, and you've just turned this into a much simpler version. Okay? All right, let's look at example 2. Example 2 says, show that cosine theta divided by 1 plus sine theta is equal to 1 minus sine theta divided by cosine theta by multiplying the numerator and the denominator by 1 minus sine theta. Okay, so in this case, I have to prove that the left side equals the right side. To do this, I don't necessarily have to touch both sides. So in other words, you could try to force this one to say this, or you could try to get this to say that. You don't have to change both sides. They've given you a hint and they've told you to prove that the left side equals the right side, multiply the numerator and the denominator by 1 minus sine theta. Well, guys, 1 minus sine theta is this denominator's conjugate. So we're going to multiply the left side only by 1 minus sine theta, and we're going to hopefully turn the left side into this statement. We're going to make the left side say the exact same thing as the right side. All right, so take the left side, cosine theta over 1 plus sine theta, and let's times the numerator and denominator by 1 minus sine theta. Okay. All right, and again, like I said, 1 minus sine theta over 1 minus sine theta, that's a well-chosen value of 1. All right, now, in the top, it doesn't always help you to distribute, like cosine theta, minus sine theta, or cosine theta. You don't necessarily always have to multiply them together. So I'm not going to multiply them together yet, like distribute. I'm just going to say that it's going to be 1 minus sine theta times cosine theta, right? Like they're being multiplied together up here, over. Now on bottom, I am going to multiply them together because usually multiplying conjugates makes some bad stuff go away, right? So let's multiply this out. 1 times 1 is 1. 1 times sine theta is positive sine theta. Negative sine theta times 1 is negative sine theta. See, they're going to cancel. And then negative sine theta times positive sine theta is negative sine squared theta. Okay, all right, so again, on top, I don't see any need to multiply them together yet, so I'm going to leave it as 1 minus sine theta times cosine theta over, they cancel, I'm left with the statement 1 minus sine squared theta. Okay, now let's pause. Remember, we're trying to get this to become that. We're trying to get this to say 1 minus sine theta over cosine theta. All right, well, they have a cosine theta in their denominator, right? I already have this part in my numerator, but this, how am I going to get a cosine theta in my denominator? Well, guys, can you think of an identity that we could take this out and put something in terms of cosine in? What does 1 minus sine squared theta equal? Guys, it's one of your Pythagorean identities. 1 minus sine squared theta is equal to cosine squared theta. So we can take this out and put this in its place. All right, so that's what we're going to do. So now on top, I'm going to have 1 minus sine theta times the cosine of theta all over. This is really cosine squared theta. All right, well, guys, now that it's attached by multiplication, what's going to happen to this cosine theta and one of these cosine thetas? They're going to cancel. So he'll cancel, the square will cancel and leave you with just 1. And then guess what you're left with? You're left with 1 minus sine theta divided by just cosine theta. And that's exactly what the right side of this equation does. So just by us manipulating the left side, we're able to prove that this really does equal that, because I can get this to become the exact same thing that is on the right side of this equation. All right, so you have proven this by making the left side become the right side. All right, now let me show you a shortcut. This is what our book doesn't always do, and I think it's worth talking about. Or if you take the exact same problem, right? Cosine theta over 1 plus sine theta equals 1 minus sine theta over cosine theta. Okay, now watch this. Our book doesn't always talk about this, but this is a proportion when one fraction equals another fraction. So if I was to cross multiply, I would get this. Cosine theta times cosine theta is cosine squared theta equals, if I do 1 plus sine theta times 1 minus sine theta, it's a FOIL, and it's exactly what we FOILed over here. And when we FOILed this, we got 1 minus sine squared theta. So when you multiply this together, you'll get 1 minus sine squared theta, right? It's the same FOIL that we did over here where they canceled and you were left with that. Now, guys, watch this. So what happens is after you cross multiply, you're left with a new identity. Now your job is to prove that this left side equals this right side. This is now the identity you're trying to prove. Can you get the right or left side to say the same thing as the other side? Well, guys, guess what? The left side says cosine squared theta. I can get the right side to say that exact same thing, because guess what 1 minus sine squared theta equals? We just said down here 1 minus sine squared theta equals cosine squared theta. So now I can say cosine squared theta equals, what's 1 minus sine squared theta? Cosine squared theta. And now you've proven that the left and right side are actually saying the exact same thing. And that is an identity. That is a statement of equality. So if you notice, cross multiplying was 10 times easier to prove this than this method, all right? But again, our book might ask you to do this anyway. I just want you to be aware of the cross multiply method will prove the exact same thing. You're just left with a different statement to prove, okay? All right, look at this one.